Hello everyone. My name is Sarah Jane Potts. I'm a research engineer for Specific, working on scaling up of perovskite solar cells and other printed electronics. And I'm here today to give you a presentation on engineering applications for the apocalypse and a little demonstration of how to make your own water filter. So, what do we think of when we say apocalypse, apart from being confined to our homes and deadly diseases? So typically when we think of this in novels and in media, the four horsemen of the apocalypse are typically referred to. These are commonly known as war, famine, pestilence, or pollution, if you've read Good Omens by Terry Pratchett, hence the reference, and death. However, these things don't just occur at end times. They've sadly existed as long as humanity and are all still seen today. So not to depress you too much, but the reality is that these things are all around us. So we still have wars going on in places like Syria. We have famine occurring across the world. We have pandemics, just like the one we're currently stuck in, COVID-19, which is confining all of us to our homes and creating weird, surreal situations like this one. And we also have pollution, which is not doing the planet any good and kind of screwing up our longevity, as well as natural disasters such as tsunamis and earthquakes, all of which grimly result in death. However, I'm not just here today to tell you about all the horrific things happening in the world, but to share with you ways in which we as engineers, and hopefully future engineers, can help us to overcome some of these problems. So what we have coming up today is having a little look at different engineering solutions for a few different scenarios. So we'll start with the one that we're all too familiar with right now, which is engineering in pandemics. Then we'll have a look at some engineering solutions for natural disasters, such as tsunamis and earthquakes. Number 3, we'll have a look at ways that we can reduce our pollution levels using engineering initiatives to try and minimize our harm on the planet, which will hopefully lead to less damage and increase the lifespan of this Earth. 4, we'll be looking at ways of overcoming famine, so engineering for developing countries to try and help those who need it most. Then we'll do a little quick summary along with some references in case there's anything you see in here today. All of the resources which aren't mine have been fully referenced, so if you want to go to the recording, or if you're in the recording, have a look at those later. You are more than welcome to do a bit of further research if you find anything particularly interesting. That's what all this is about, trying to empower people to find more. And then finally, we'll be ending on how to make your very own water purification device there in your very own home, just using what hopefully you can find around the house and the garden. So let's start with what we're all too aware of at the moment. So pandemics. These exist throughout history, so it's not just what we're having to go through right now. So to give you a brief overview, probably one of the most well-known ones in history was the bubonic plague of 1337. This resulted in tens of millions of deaths all over the world in around only 5 years, which then lingered throughout centuries, resulting in epidemics such as the Great Plague of London in 1665, with treatment only becoming developed in 1894, and the final treatment only being produced in 1947, so not all that long ago. This was a truly horrific pandemic, which hopefully what we're seeing right now will not go anywhere near. But with modern medicine and our technological advances, this could have been substantially less horrific. So more recently, we turn to something that was in my lifetime, probably yours, which is influenza A H1N1 in 2009, known commonly as swine flu, which according to the World Health Organization resulted in around 100 to 400,000 global deaths in the first year alone. So not that dissimilar to what we're having to go through right now. However, the vaccination was actually developed pretty quickly, as only 2 proteins in the vaccination were different to our typical flu vaccination. So to match the virus that they were having with the vaccine, they only had to change a couple of things, making it available by October of that year, only a few months after the pandemic was declared. However, due to the typical problems, production of this was not particularly fast, and the pandemic ended up lasting until August of 2010. And now we bring ourselves to what we are all painfully too aware of, which is the severe acute respiratory syndrome coronavirus 2, known to most people as COVID-19 or simply coronavirus. So when this presentation was written, there were around 3 million cases, resulting in around 200,000 deaths. The designing of the vaccinations are actually currently in progress, but as the virus is quite different to what's previously been tackled, it may take a while. However, to try and minimize this in the meanwhile, there are ways in which engineers such as myself are currently doing our best to help not only those who are ill, but also help our fantastic emergency services. So, COVID-19, what is it that we are doing? Even just at my university, most of these things are currently being looked into or done. So I myself have been working on face shields and creating hand sanitization gel, but there's been a lot of other things done. So if we start with PPE, which is something which we currently had in shortage, although looking a bit better now. So face masks. What form of engineering is this? So this is mainly mechanical based engineering design. So if you were to want to make one of these for yourself, you could either do it using a laser cutter, or you could use a fusion deposition modeling machine, such as the one I have downstairs in my house. So the way this works is we take a filament such as PLA or PETG, which then goes through the nozzle, it's heated up, in this case to around 210 degrees, until it's liquefied, or just beyond glass transition temperature, so just until it's malleable, and then it gets squirted out and built up in layers until we have our mask. So for this, we're just using basic computer-aided design techniques. So if you want to have a go at this at home, you are welcome to use some existing freeware softwares, which are good enough to make things like this in. So what are the advantages of using rapid prototyping, so 3D printing? It is incredibly low cost setup, but it takes an absolute age. So this face shield you see there, just the head section, that took around 4 hours to print off. So if we compare that to alternative techniques such as injection molding, which takes seconds to produce, it's not so great. But considering the injection molding costs hundreds of thousands, if not more, pounds to get the equipment, something that's only 200 quid off of, I won't say the website, but off the website many of us use quite regularly, is something far more viable for these sorts of situations. So another thing which I get to do, and I will actually be doing tomorrow, is manufacturing hand gel. So this is a form of chemical engineering, which is incredibly useful right now for trying to keep people clean, help our National Health Service, which are already risking their lives, and trying to do what we can so that we can minimize the effects of this virus, as the outer layer of this virus can be, the fatty layer can be removed by using things such as hand gels and soap, which means it's incredibly effective in comparison to not using it at all. So what is it made up of? So the hand gel I'm currently making is a mixture of ethanol, which is an alcohol-based solvent, with glycerol, and then hydrogen peroxide. So in here we have our batch of ethanol and glycerol. This is actually a 500 litre container. We get through this every single day at the moment, so it's pretty good. We're pumping the stuff out. And then we have some pumps over here to pump in our hydrogen peroxide. And on the other side here, just out of the camera view, is a similar container of the exact same size containing distilled water. So when all of this comes together, it goes through the pumps, down taps, and into our containers, which I then have the joy of putting hundreds of caps onto in a row. But it's actually rather painful manual labor, but I'm really happy we can make a difference. And then that goes over to the labeling station, where they are cleaned down, labeled, and put into crates for storage, and then transported to those who need it most. But big thing which has been in the news is ventilator systems. So So the case of ventilators, which are used for assisted breathing by pumping oxygen-rich air into patient lungs, a lot of effort has been made both at lab scale and in industry. In the case of research institutes such as the Institute at Swansea University, they have been working on prototype designs with support from health boards and industry, as well as conducting modeling such as computational fluid dynamics for continuous positive airway pressure devices, which enables us to understand how the air actually flows through devices, understand the pressure gradients, and understand how these things interact, so you can improve the design to make it work more efficiently and more effectively and at a lower cost. Meanwhile, after being contacted by the government, manufacturing industries such as Dyson and Renishaw have started utilizing what they have in their own manufacturing facilities to develop ventilator systems and components, where Dyson has been working on their own new ventilator called the Covent, whilst Renishaw dedicated part of its manufacturing sites in Gloucestershire and some of them in South Wales, produce precision machined components for 2 different ventilators at the moment, manufactured by a group called Ventilator Challenge UK. So these are really good things, but to go a little bit more into the engineering design, one that I found particularly fascinating is Dyson's Covent. So after being contacted by Boris Johnson, Sir James Dyson had Dyson both develop and create the Covent ventilator within only 30 days, which is quite an impressive turnaround time for engineering designs. It was designed with Dyson from the help of TTP and outside experts from medical and healthcare product regulatory agencies such as MHRA, as well as the NHS. So all of this was created with the user and the actual operators in mind. So after this was done, you produced a ventilator which was efficient in conserving oxygen, that was bed mountable, so unlike most, it's actually portable where required, doesn't need a fixed air supply, and was built to address actual clinical needs for COVID-19 patients. And as it's battery powered, with quite an easy user interface, it's pretty straightforward, and the design is also equipped with the usual Dyson motor and air purifier, which enables Dyson to take the technology they know and understand and adapt it to this particular situation. However, for those of you who have looked at the news recently, you'll find out that the UK government has decided they no longer need the 10,000 units. But quite nicely, Dyson had no regrets, and although they invested £20 million of their own money into this, they are going to do what they can and even donate some of their ventilators to those who need it most. So although these are pretty horrible times, we are getting engineering advancements in it, which can then help us in the future for other problems. So it's always thinking about those things. Another thing which has been happening, which you'll probably also see on the news, is the use of AI and robotics. So in China, these have been used for screening procedures, using infrared cameras to produce thermal mapping in airports, on drones, and even on police helmets. However, there is a limit to infrared imaging, as it can only show an external body temperature, which doesn't always account for the effects of exercise, hormonal effects, where alternative thermometers, which can actually go in the body, like in-ear thermometers, can actually give a better reading. So great tech, but could be used in a better way. So for one example, the drones could be used for far better things, such as delivering items such as blood, medicine remotely to those who really need it. But at the moment, we do not have the infrastructure in place. So in order for these things to become part of our future, someone needs to create air traffic control systems alongside security systems to prevent hacking or theft, so that they can operate at a scale where both the aircraft doesn't interfere with one another or existing planes which are in the air. But these do provide us with new methods and new ideas to try and develop other products. However, just to make it clear, infrared cameras are something, if you ever get really interested in developing your own, can just be ordered online. So what I have in my hand is a small FLIR infrared camera, which can be strapped onto my phone, which I actually used in a previous demonstration for looking at heated up coasters. So these are quite easy to access, and as you can see, it's quite small, so it could easily be fitted onto just about anything. So it does provide us with opportunities to have developments in engineering design, as always. So moving on to the second section, where we're going to be looking at ways in which engineering can be used to tackle natural disasters. So when I say natural disasters, I'm referring to things which are out of our control, forces in nature due to the way our tectonic plates move. So things like earthquakes, volcanic eruptions, and tsunamis. And in this session, I'll be focusing more on ways we can do cleanup operations for earthquakes and tsunamis, although there are lots of monitoring methods now in place with artificial intelligence involved to enable people to predict when these things are going to happen, such as volcanic eruptions, so that we can minimize their effects. However, although you get the heck out of the way when a volcano comes, sometimes it's not always possible with earthquakes if they come on suddenly. So we're just going to look at ways in which we can help people after they happen. Or we can also look at ways in which, even when they're happening, we can minimize their effects. So usually in earthquakes, a big contributor to some of the disasters you see are due to buildings collapse. This is due to the fact that during an earthquake, vibrations from seismic waves can cause buildings to excessively sway beyond their deformation limit. And this can lead to them giving out, collapsing, and resulting in a lot of deaths, sadly. But there are a number of ways to reduce these effects on buildings' structural integrities. For starters, adequate truss structures can be used. So when I say trusses, I mean beams which are put at different angles to each other, so either in crosses or in triangles, to improve the stiffness and the strength, both laterally and vertically, of the buildings, so that they can withstand greater loads. You can also have things such as shear walls, which are vertical walls that stiffen the structural frame of the building and help it to resist the rocking forces. Although both of these things can limit the flexibility of a building design. So in some cases, moment resisting frames where beams and columns can actually bend together can be more useful, which enable the entire building to move in response to lateral force. Not that I think I would want to be in one of those buildings at that point. I think I would be sick. I get sick in a car, so I don't think that would be great, but it's a fantastic method for enabling a building to withstand these forces without giving out. As well as this, buildings can also be isolated from the ground. So base isolators, which can be put like a pair of stilts underneath the building, connecting the building to the ground, can be applied in a variety of bearings, springs, padded cylinders, or if you want to apply something to enable it to sway in something like a skyscraper, which is higher up, you can also have tuned mass dampening systems, which we will talk about a little bit more later. So what we have here is what we would typically get into the building in the form of a lead rubber bearings. So these bearings are usually used where you have bearing pad designs containing a solid lead core, which is then wrapped around in alternating layers of rubber and steel. The lead core ensures that the bearing is rigid and robust in the vertical direction, whilst the rubber and steel keeps the bearing flexible in the horizontal direction. And these bearings are attached to the building at the foundations using the steel plates, so that the foundations can move freely without affecting the building. However, for this to be effective, you need stiff ground with deep foundations and driven piles. Otherwise, it can still vibrate, but this can be incredibly effective, and there are multiple methods available for this. So what I have next are two particularly good examples of where you've had really, really good seismic proof building structures. So the first one is I apologize for my pronunciation, the Taipei 101 Tower, and the second is the Philippine Stadium. So the Taipei 101 skyscraper is located in Taiwan, and it uses a tuned mass dampener, which is simply a very large metal ball, and this is based between the 87th and 92nd floors. This enables the ball to swing a little bit like a pendulum to counter the transient loads of the earthquakes and thus reduce the sway of the tower. So this tuned mass dampener is supported by hydraulic viscous dampener arms and a bumper system, which operates a little bit like your car suspension, so that when the large seismic waves act upon the building, the tuned mass dampener will sway in the opposite direction, damping out the forces and bringing the building hopefully back to equilibrium to minimize the shake and therefore prevent it from collapsing. On the other hand, the Philippine Arena is constructed out of a concrete lower level and a steel upper section with a series of truss structures and tension rings which add suitable stiffness and strength to the frame, thus minimizing its ability to move. As well as this, the two layers, so the concrete lower and the steel upper, are joined by lead rubber bearings, previously seen on the other slide. This enables the base and the foundation system to freely move without affecting the steel upper structures, therefore minimizing the effects and preventing it from collapsing in, hopefully. So moving on, in the case where this does have horrific effects and things do collapse, which we can't always prevent, we can also utilize technologies such as rescue robots. So there are a variety of robots available at the moment which are designed to scout out, find people, or identify life and help where possible. So we'll start with Quince, which was designed by Chiba Institute of Technology and Tohoku University. So this was designed for exploring, to have a look around a variety of terrains and identify where people were, and also to deliver supplies, as it has a few arms that things can be attached to when in disaster zones. It also has a few detectors attached to it, so it can detect things such as carbon dioxide, breath, and heat through infrared cameras, which enable it to both identify people and have live feedback to its operator, so they know where they need to go to actually help those in need. A similar system is iRobot's PackBot 510. So you've probably heard of iRobot before, as they are quite famous for the Roomba vacuum, which is very great, it's very cute, very great, but this is actually incredibly useful in disaster zones. So these PackBots were developed to assist with the Fukushima Daihatsu nuclear power plant disaster, which happened quite a while back now. But when that happened due to an earthquake, people were not able to access that building. They couldn't check what the damage was like. So they sent PackBots in, which were capable of detecting temperature, gamma radiation, explosive gases and vapors, as well as toxic chemicals, to properly assess the situation. And then you get live data fed back to the controllers so that they could understand what needed to be done next. So these things were really crucial when they were trying to assess the initial situation and come up with a proper strategy on how to move forward. And similar systems are now actually used by the military in war zones to try and identify bombs, try and find people in need, and also to try and help in situations where people might be vulnerable. A very well-known system is Atlas, which is the most humanoid-like one out there, and has an agility which I could not compete with. I mean, I can't do a backflip, but he can, which is a little depressing. It's a robot. These were designed by Boston Dynamics and can perform a variety of skills, whether it's running, jumping, flipping, or doing parkour. So if you are interested in seeing a robot doing parkour, look at Atlas. And as well as doing cool things, it's also designed to do life-saving tasks in a variety of dangerous conditions. So it has the mobility in its hands, flip switches, shut off valves, it can open doors, it can look after different power equipment. So anything where you need human activity, where you actually need that mobility to turn things on and off, move in and out, Atlas has the ability to mimic that, which is really cool. Another one which I found particularly cool was this robotic safety crawler design, which is designed by the Japanese city Yokohama's disaster recovery department. The idea of this robot's actually really cool, as it provides transport in a variety of terrains for those who are injured. It's a little bit awkward to look at because it's pretty much a casket on wheels, but it's for living people. So it will take the injured patient, put them into the container, and then the container will go inside its shell, enabling them to be transported as safely as possible without causing any further damage in areas where humans would not be able to get to them, never mind with a stretcher. So these are some really great responses to these disasters. Looking on to one which is particularly pressing at the moment, particularly before we had COVID-19, but hopefully it will become a hot topic straight after, is how do we produce our pollution? So in this one, I'll be looking at ways in which we can clean our waters, which will be covered a little bit more later, but in a different aspect. So this is, for this case, looking at how we can clean our seas and our rivers to remove a variety of litter and microplastics. So in this, we'll be looking at some chemical, UV and magnetic treatments, as well as some existing robots. I'll also be giving a brief overview of circular economy. So what is it and why is it really useful to try and minimize our carbon footprint? And then lastly, on the same theme, is how we can decarbonize by switching to sustainable energy solutions and also applying the circular economy. How can we make sure that that, even when it's over, doesn't have a lasting effect? So we'll start with how we can decontaminate our seas. So we have a variety of examples here. So I'll start with some of the robot bots which were designed to remove existing litter in our seas. So one of my particular favorites, maybe due to its rather adorable eyes, is Mr. Trash Wheel, who works by using a rather simple system. So it's just a water wheel attached to a conveyor belt. So as the water wheel is spun, just by him moving around in the sea, it will enable this conveyor system to rotate around and transport the litter on little ridges from the sea into a humongous skip which is located in his rear, which can allow him to collect quite a lot of rubbish in one turn before he has to come and offload and then go back in to get some more. Another cool design, but instead of using a water wheel, using a solar system which is capable of going further out to sea, is Seavax, which is a robotic vacuum ship created by Bluebird Marine Systems Limited, which can vacuum apparently up to 50 tons of rubbish at a time. It is increased when used alongside something else they have called CNET, which increases that capacity so it doesn't have to come back in as often. It is sustainably powered, obviously, by using a series of solar panels, which enable it to treat up to, hopefully, 90 million litres of seawater a year. So when you combine these sorts of things together, it can start to reduce the amount of plastic in our seas. However, although these methods can remove larger bits of plastic and other bits of litter in the sea, alternative methods are required to clean up the smaller particles or oil. To tackle this, the FemLab accelerator physicist Arden Warner came up with a solution of adding little bits of iron filings or magnetized dust to the water contaminated with oil, and then these will magnetize the oil, combine with the oil, and then enable it to be removed with magnets. A similar idea was then implemented by an Irish teenager called Fionn Vieira, who went on to win the 2019 Google Science Fair due to his design, which used pretty much the same technique but applied to microplastics. So you would then add a little bit of oil to the water containing the microplastics, and then once again add the magnetite powder, and then using the magnets you could remove both the oil and the microplastics, which would then migrate into the layer of oil, enabling all of it to go at once. So these are some really good methods. Another method for water purification is using chemicals and UV light. So a solution which was created in my group Specific at Swansea University, which can be read more about on the Sunrise website. So there is a reference to this at the end. Used a combination of titanium dioxide, which is a little white pigment that you actually have used in a lot of things. So if you've eaten chicken nuggets, the reason they're white is because they're dyed with this stuff, so it's pretty safe. But in this case, it was used to remove pollutants from water when in the presence of UV light. So this could either be artificially or in natural sunlight, which enabled it to be used in developing countries, hopefully. In this example, the titanium dioxide is coated onto a glass fiber sheet. And then when subjected to UV light, will promote the titanium dioxide nanoparticles to go to a higher energy state. So for those of you who saw my batteries talk, or if you haven't, check out later, it enables them to react in a similar way and excites them to a higher energy state. And when this happens, you are left with a positive charged hole and a negatively excited electron. And this enables the TiO2 to react with water and oxygen, which creates hydroxyl radicals. And these are capable of tearing apart the pollution molecules and producing gases such as nitrogen and carbon dioxide. Therefore, this can be used to kill off the bacteria like E. coli and viruses like HIV, which means it can be used as a really good technique, which is relatively simple and straightforward, just by coating the TiO2 onto a surface with the water flowing over it in sunlight. So moving on to something which is a little bit deeper, but incredibly useful. So circular economy. All of you would have heard of it in some way or form. So when you hear the words reduce, reuse, recycle, that's referring to circular economy. So circular economy is another way of thinking. Instead of just creating something for a single use, you design into it the ability to either be maintained and prolonged for a longer period, such as people who are now putting out phones which have the ability to be taken apart and have single components replaced at a time, rather than having to scrap your whole phone. The ability to reuse and redistribute, so making things that they can be given away, so like with clothes, giving them to a charity shop, giving them a new life, upcycling them, those sorts of things, and moving down to refurbish and remanufacture. So in this case, it's a bit like with your bicycle, being able to improve its design. And then the final port of call, not the first one, is then recycling. So this way of thinking enables engineers to start to change designs so that it's not just a throwaway economy and it's not a throwaway product. We have to start being able to make them used multiple times or used in different ways and prolong their lives. And in times when you can't keep something going, then you should be able to at least recycle it. So these are things that have to run through a lot of people's heads. It's running through mine right now. When we are creating things like the solar cells, we have to try and consider, how long is this going to last for? What other uses can I have for it? And can we extract these parts afterwards so that they can be given new life? So this is quite a deep one, so I'll give you a little example on how this can be applied in the next slide. So on this one, I'm just going to talk to you about something which a lot of people know, which is decarbonising our energy. So in the case of Specific, we are working on things such as solar cells. There are tons of different types of solar cells, but the one I'm working on are called perovskites, which are a little bit more suitable in our slightly gloomy British weather, although it is relatively nice out there today. As well as this, you've also got wind and form of wind turbines, and also the new vibrating designs, which I'm awaiting, and then hydro and tidal, and a variety of other applications. So by now, we were hoping to have had at least 30% of our energy taken only from renewables. So these stats were actually done yesterday. It's not amazing, but admittedly it was raining. So normally solar makes up for quite a bit more than that. But if you want to check it out or even see how this varies, you can just go to electricinsights.co.uk, and this updates every day, quite regularly. So not only can you see where all of our energy is coming from at the moment, but you can also know how this relates to our demand, how this relates to the cost, and also whether we're improving our carbon emissions. So all of these things have to be taken into account. And hopefully as time goes on, these will start to take up a bit more space. But this will go to my other talks, which some of you will hopefully have seen, which is we need batteries. We need to be able to store this energy and use it more effectively later on. But we'll talk about that more later. So finding ways to produce devices in more environmentally friendly ways are also needed. So referring back to the circular economy, we need to find alternative materials. So in some solar cells, things like rare earth materials are regularly used. These are resources we don't have a lot of and therefore need to protect. So it's always finding alternatives and finding better ways to do it, or even finding ways to reduce our travel, to reduce our carbon footprint. So finding things locally. All of these things have to be taken into consideration and don't just have to be at an engineering level. We can even do it in our own lives. And then going down to the final part of the circular economy, which is recycling. So this can be applied to things such as wind turbines. So wind turbine blades are made of fiberglass, which can be quite hard to recycle, as it's not the nicest of materials to deal with. However, there are companies currently looking to take these old wind turbine blades, because wind turbines can last for a couple of decades, or potentially more now. But after that, after degradation and wear, they do, after a while, have to be wrote off for our own safety, because you don't want a deadly blade going around in the air. But they can be given a new life. So in this case, they are being turned into pellets, which can then be used to make fiberglass boards for civil structures, as well as injectable plastics. So they have a lot of new uses. So these things have to be thought about beforehand, though, not just after you have to write them off and go, oh dear, what the heck do I do now? So all of these things should be running through the head of an engineer or a future engineer in some of your cases, hopefully. So the next topic is overcoming famine. So famine is a humongous problem we have in so many different countries, not just in developing countries. We sometimes even have it here. But as well as looking into the politics of how we distribute our food, we also can look into ways of improving the ability for people in places such as developing countries to create their own foods. So I'll start by looking at hydroponics, which is a method of soilless plant growth. I will also be going through some off-grid energy supplies. So how do we give energy to these places so that they have the ability to cook, they have the ability to live a more typical lifestyle. Also look at some alternative cooking methods which can be used in nice, hot, sunny places without our typical energy requirements. And then looking at water purification, as that is really important and needed for good sanitation and good health. So if we start with hydroponics, hydroponics is the science of growing plants without using soil. This works by feeding them on a mineral nutrient salts, which are dissolved in the water or produced in alternative ways, while supporting the roots of the plant in some form of inert structure or floating them in water. It can be used for things like living walls, roof gardens, or a variety of growing situations. And it's not really a new technique. This has existed back when the ancient Egyptians were around. They were utilizing this. So it's something that we should be introducing more now. And where places such as developing countries don't have access to soil needed for conventional farming methods, this is incredibly useful. As it has the ability to produce a range of vegetables such as tomatoes, peppers, from spring to autumn when in natural light, or all year round if you have the ability to use artificial light sources. So if we go through a few examples, a few techniques used include deep water culture. So this uses styrofoam boards which have drilled holes through them in which the roots of the plants can then float freely. This enables the plants to have access to well oxygenated nutrients in the water, which would be supplied in some form, and really good for leafy greens that require little root support, but isn't always applicable for all applications and requires quite a lot of water. An alternative route, one of my favourites, is where you utilise both the ability to farm fish as well as plants in the form of aquaponics. In this case, the fish provide the fertiliser for the plants, and then the roots of the plants filter the water for the fish, so they work quite nicely in harmony. As with the freshwater source, this enables the fish to give off ammonia through their gills and excrement, so their poop. And this gradually nitrifies the bacteria, this gradually nitrifying bacteria grows on the surface of the water, just underneath it, and then gradually converts the fish waste into nitrates. And these nitrates can then feed the plants. Therefore, with a suitable ratio of plants to fish, both can be effectively farmed and both can exist happily side by side, as was done using slightly different containers, obviously, but back when the Egyptians were around. So these are very suitable techniques which don't require too much human intervention if set up well. An alternative system is also the drip system. So to minimize the water required, grow mediums with high water retention, such as coconut fibers, expanded clay, perlite, rockwood, sand, cocoa, peat moss, vermiculite, quite a few things. So anything which has a high water retention can be used to hold the root systems in place. This is a simple technique where a pump on a timer delivers a flow of water on a slow feed through pipes, with the nutrient-rich water being supplied at the base of each plant through individual outlets. This excess water can then either be returned to a reservoir and reused, or not collected according to the setup. When working well, this method can be very low maintenance with a very good high output. But the addition of synthetic nutrients to the water is sometimes required to avoid the pipes from clogging, which can happen with some natural sources. Although with such a large range of methods available, so there are other things on top of this as well. If you want to know more, you're welcome to check out the references I've put down. This offers quite a good method for farming in areas which would not be able to do it otherwise using traditional methods. So moving on, in order to have an energy supply in areas which are quite deserted, so in developing countries, we can also put in off-grid energy systems. So the one you see here was created in Zambia by a group from my research institute, Specific at Swansea University. So this structure has a solar PV roof, which is then put on stilts, and then has a battery to enable it to have a supply so that they can still utilize the energy even during the night time. So they also have little independent solar lighting around it as well, so that it's a nice community centre where people can utilize it, come together and have access to energy so they can charge their phones or any device they require, and even use it for cooking. Although there are alternative forms of cooking which are suitable for developing countries. So some of my favourite ones are solar-based cookers. And there are a few designs for this, so I will focus on the two main ones and then also have a look into a commercial design. So as traditional fuels and electricity are quite scarce in some developing countries, alternative methods such as these enable people to cook food at pretty high temperatures. So the parabolic and box solar cookers are regularly used and a great solution in sunnier countries. The parabolic reflector solar cookers work by reflecting the sunlight onto a concentrated spot, in this case the food, using a series of reflective surfaces positioned in either a trough or satellite dish shape, which directs the light beams into the desired position. For example, the parabolic solar dish has been used by one group to produce a bread oven designed by a group of students in the Norwegian University of Science and Technology, with the main purpose being able to reach 250 degrees centigrade. This enables it to bake bread and create foods which are traditionally eaten in places like Ethiopia for where it was designed. So this is a really good use. And then we have simpler design, which are the box cookers. These consist simply of a box with black insides, which can be painted or just from black coating. This enables it to absorb and retain heat in with a transparent glass lid, enabling the light beams from the sun, so the instant light beams, be able to transmit their way through, with other beams being reflected from the reflective panels into the box. And overall, this means that it's quite straightforward, relatively easy to make. I imagine if you are bored at home, have a bit of glass, a suitable box and reflective panels, you could have a go at making one of these in your garden, and has the ability to still reach pretty high temperatures and requires a lot less effort than creating a parabolic cooker. But there are other designs, although these may not be as useful in developing countries. If you were to buy one here in the UK, which has the ability of heating up in our lovely sun conditions, then you have things like the Go Sun solar cooker. This is a cooker which combines heating via the parabolic reflection, as seen in the previous slide, with an evacuated tube cooking chamber into which 2 cans can be loaded in a similar manner to an industrial tube furnace, or solar hot water heaters, which you'll see on some roofs, which can be used for heating water used for your baths, your taps, and things like that. The tube consists of 2 layers of borosilicate glass with air between them, as with double glazed windows to enable heat to pass through, but stay nice and warm inside. The internal face of the tube is coated in aluminium nitrate to absorb heat, stainless steel to evenly distribute heat, and copper to reflect the heat as infrared radiation back into the tube. Overall, this enables the tube to trap UV and visible light and enable the inside of the tube to get really nice and hot. While the compound parabolic reflectors, which in this case I believe are motorized to move around the sun, have the ability to focus more light onto the tube from a range of angles. So this enables the vacuum tube and parabolic heater combination to reach temperatures as high as 250 degrees C, as with the parabolic cooker, but in far weaker light conditions, and remain hot for long enough duration to cook due to its vacuum and insulated surfaces. However, the vacuum tubes are substantially more delicate than just using parabolic reflectors and a cooking pot or a box, as when they are dropped or even misused, and even if they're preheated for too long without anything in it, they can become damaged, fractured, and then are pretty useless, making it great for camping, but not so great for developing countries, and also not so great for anyone who's particularly clumsy, so I may struggle with it. But moving on to other issues, so something that we will be looking at quite a lot more in a bit is water purification and sanitation. So when I'm referring to it here, these are looking at commercial methods which are really useful and reliable at removing contaminants. So the first one here is the Life Straw, which is a small portable filter which can be used up to 5 years using a microbiological hollow fiber membrane that filters up to around 0.2 microns. This is capable of removing most bacteria and particles and microplastics so that the water is clean and drinkable. Another product is the Life Sack. So this is able to be used as a backpack and uses a solar water disinfection process where UVA radiation and thermal treatment work in combination to kill toxic microorganisms and bacteria, also enabling the water to become drinkable, but using a bit of a different method. And then we have one of the simpler methods, but potentially just as effective, which is the solar ball. So this design is capable of using solar rays to purify water. So how this works is sunlight goes in and heats up the dirty water, and this leads to the water forming condensation on the roof of the ball, which is then guided down a spout via an internal gutter system that runs along its diameter, and then collects clean water where the contaminants are left behind in the other chamber. This ball is capable, apparently, of producing up to 3 litres of drinkable water per day, which is really impressive. And if we were to finish off our filters, we would use a very similar technique, where I will show you later. Or you can simply, once it's had all the stuff filtered out of it, boil the water, which will also remove a lot of contaminants. So to summarize, we have apocalyptic style disasters throughout history and now all the time. But there are ways in which we can minimize their effects. So engineering solutions can be used to overcome a lot of different problems when used to tackle things ranging from natural disasters to medical responses, to being able to find people in need, or even being able to engineer new ways which people can grow food, cook food, and purify water, all of which have a humongous impact on reducing a lot of unnecessary deaths. So if you were to come into this field, you would have the ability to really make a difference and to help those in need. And we need more innovations, we need more inspiration. So although we get some bleak times, hopefully it helps us to come together. So enough of that. Now it will be time for you to make your own device. So have all of your things to hand. But in the meanwhile, if you would like to have a look at any of the things we've cut that have been covered in this presentation more, I have my list of references. So there's quite a few of them, but this can be paused at any point and look back over, and you can go into any of these to do a bit of further research. But in the meanwhile, let's move on to the demonstration. So today we are going to make a water filter out of everyday items. So if I tilt my screen down slightly, you'll see I have my water bottle, which I have already cut into 2 pieces. So we're going to take, so I'll give people a little bit of time to get their scissors out, and please be safe when cutting. And just make sure it's nice, clean, and don't get your hands anywhere in the way. But once you have it cut, you can then get the base at the bottom and place the top upside down inside, so that after we pour the water through all of our layers, we'll then be able to get to collect at the bottom. So whilst people are cutting, I will just go through what's shown on the demonstration. Our filter we're making today will consist of several layers. So this will have rocks and pebbles at the top, working down to finer particles like sand and charcoal, and then moving down to either cotton pads or some cloth, with the idea of this being able to catch any of the smaller particles and prevent them from passing through to our filtered water. You may have to pass this through a few times to ensure all of it's collected. So this enables us to get rid of smaller and smaller bits. However, if you want to drink this, you do need to do an extra step. So once it has been filtered, you will need to either boil the water, get rid of any of the other contaminants which we can't filter out, or use a similar system to what was done in the solar ball by having a dome or a bowl around the top and then a container at the bottom, from which you can enable it to condensate and then reform at the bottom without any of the contaminants. But today, if you just focus on getting it to a clean level, visually clean level, you can then work on the filtering systems afterwards. So if I unshare my screen, you will now be able to see what I am working on. If you have a look right here. So here is my bottle in two parts, one inside the other. And now, get a little bit lower. I'm going to start with my lower levels. So this will be things like cotton pads or a bit of cloth, which you can use an elastic band to tie onto your bottle cap, but I'm going to be using cotton pads so they can just get stuffed down here. So we'll put a few of these in the bottom and just stuff them down the there we go. Have a few of these just to pad it out and make sure the water has to pass through our pads. So I'm going to fluff them up a bit and have them all around to make sure that the water definitely passes through them. And the next thing I'm going to use is my sand. I've got a little bit of chocolate in there as well. So I'm going to now pour that in. You may also need to rearrange bits as you go. So as you can see, it may have slightly moved my cotton pads. So I will then move these around, get my sand nicely nestled on top. There we go. So this is 2 layers. So we've got cotton pads, then our sand. Now we're going to move on to the small pebbles, or whatever else you have. So these are my smaller pebbles. I'm just going to pour these in and move these about. There we go. And then to top it off, I have some large pebbles. And if I pour these in, we now have several layers through which our dirty water. So if I put my dirty water on screen now, that is pretty nasty, full of dirt and random bits from my garden. When that passes through, the big bits of dirt and other parts will get stuck at the top, with smaller and smaller bits getting removed as we make our way down towards the bottom. So to demonstrate, just to do a recap, so that's cotton buds, there's sand and pebbles, maybe a chocolate in the middle. Get it properly in camera. Yes, there we go. Pebbles, smaller pebbles, sand, cotton buds or cloth. And that should be all you need to get your water looking a lot cleaner. So if I get this in place, I can now pour this in. So you see my dirty, dirty water going in. You can see the colour of it. It's not particularly nice. And now we wait. And what you can see, if I hold it up to my camera, hopefully without going on my hand, is the water is looking a bit clearer as it comes through. However, my water is very dirty, so this may take more than one attempt. So once that starts to pass through, wait for it to go through all the way out, and then you just put it back in. And now, over